Hey guys, Jake here, coming at you with another math lesson today. This time we're doing it a little different though. We're doing it live. At least I hope we're live. I think we're live. If everything's working the way it should be, we should be good to go. So today we're going to be going over some implicit differentiation and related rates problems I got here for you guys. Of course, if you got any questions along the way, feel free to drop them in the comments. I'll do my best to answer whatever questions you have along the way. And let's go ahead and just jump right on into it here. So we're going to get started with this question here. We're going to start with an implicit differentiation problem. So we're going to find dy dx by implicit differentiation. And we're going to do that with this equation here, which is sine of x plus cosine of y equals sine of x times cosine of y. So first of all, a couple things to think about when you're doing an implicit differentiation problem. You always want to look at, in this case, it's telling us to find dy dx, which has a lot of information in itself right there. So you can look at when you have this d something over d something, whatever letter is here on top, you're going to want to treat that as your function, and whatever letter is here on bottom, you're going to treat that as your variable. So right off the bat, we already have some information just based on the question and what it's asking us to find, that we know we're going to treat y as a function and x as a variable. So the reason why that's important is we don't actually know what y is. And based on the equation that we are given here, we can't solve for y and figure out what y is. So we're not actually going to be able to, use typical methods of finding derivatives to find the derivative of y, since we don't know y. But when we're finding the derivative with respect to x, because in order to find dy over dx, we're going to have to find the derivative with respect to whatever our variable is. So that right there tells us that we're going to be finding the derivative with respect to x of both sides of our equation. So when we find the derivative with respect to x of our function y, which we know is a function of x, there's going to be a little bit of a trick that we're going to have to apply when doing that. So I'll kind of get to what that trick is when we get to that point in the problem, but let's go ahead and just kind of start with each side of our equation here. So first of all, to find the derivative with respect to x of this whole equation, we can kind of just break it down, term by term, basically. Think about this piece here first, then the cosine of y piece, and then this sine of x times cosine y. So first of all, to find the derivative of sine x with respect to x, that's going to be a derivative that you probably want to just memorize. The derivative of sine x with respect to x is just going to be cosine x. There's really nothing special there because this term right here only has x's, which we know is the variable. So as a result, we can just use standard derivative methods to find the derivative of that one term. Okay, so then this next term here, cosine of y, we are going to have to do something a little bit different there for that one because this has a y in it, which is, like I said before, our function. So as a result, when we're finding the derivative of that function, which we don't know what y is in terms of x, we just know that it is some function of x. What we're going to have to do is use the chain rule to find the derivative of this term here, because when you look at this term here, this basically is a composite function because we have a function y, which is plugged into another function, which is the cosine piece. So when you're looking at this cosine of y, we have to use chain rule where we have y being our inner function and the cosine being our outer function. So as a result, the derivative of this term here, cosine of y, like I said, we're going to have to apply the chain rule, which just says that we're going to do the derivative of our outside function. So the derivative of this cosine piece, the derivative of cosine is negative sine. So actually, this isn't going to be a plus, it's going to be a minus because it's minus sine. So we're going to have minus sine. And chain rule says to do the derivative of the outside term, leave the inside term alone. So we're going to leave our y as y. And then we have to multiply that by the derivative of our inside term. Well, the derivative of y we don't actually know because we don't know what y is. If we don't know y, we can't know the derivative of y. But since we're trying to find the derivative of y with respect to x, basically what you want to think about is what is some symbol or terminology that literally just means the derivative of y with respect to x. And that is exactly what dy dx is. So when you're taking the derivative of another letter, which you know to be your function, with respect to a different letter, which you know to be your variable, that's just going to be represented as, d of whatever your function is over d of whatever your variable is. In this case, dy over dx. Then for the right side of our equation, we're going to have to do the product rule here because we have sine of x times cosine of y. So we have these two separate terms being multiplied together. So to do product rule, we kind of want to create like a little side problem out of that basically. So I'll just kind of go over here for a second. And we want to basically designate which function is going to be f, which we'll just go ahead and say is going to be sine x, and which function is going to be g, which we'll go ahead and say is cosine of y. It really doesn't matter which one you call which, as long as you're consistent throughout this little product rule subproblem. Then we need to find the derivative of each of these terms. So derivative of sine x, just like we found over here, is just going to be cosine of x. When you only have your variable, there's nothing weird you need to worry about. But then to find the derivative of cosine y, again, we're doing the derivative of cosine y with respect to x. So we actually already found that right here. Remember, the derivative of cosine y with respect to x is going to be negative sine of y times dy dx. All right. So now the product rule says that we're going to basically have to cross multiply these. So we do the derivative of one function times the original of the other one, and then add those together. So f times g prime, f prime times g is going to give us sine of x times negative sine of y dy dx. So that'll just give us negative sine of x times sine of y dy dx. And then we're going to do cosine of x times cosine of y, and then add that in. So plus cosine of x times cosine of y. Okay, so now, as I've done with a lot of the other implicit differentiation problems on my channel before, the next thing, once we've actually taken the derivative of both sides of our equation, which we've done at this point, the next thing we want to do is basically move all of our dy dx terms over to one side of the equation and all of our non-dy dx terms over to the other side of the equation. So at this point, we can go ahead and do that. We'll just go ahead and move all of our dy dx terms over to the left, and then all of our non-dy dx terms over to the right. So you can see this term here, cosine of x, does not have dy dx in it, so we'll subtract that from both sides. And then this term here does have a dy dx in it, so we'll move it over to the right. So since it's a negative, we can just add that term to both sides. And we will want to add that over here as well. So what that's going to do is it's going to cancel this term on the right side. It's going to cancel this term on the left side, and we're going to have sine of x times sine of y times dy dx, and then minus sine of y dy dx on the left side of our equation, and on the right side, we're just going to have this cosine of x times cosine of y minus cosine of x. Okay, so now once we've gotten all of our dy dx terms on one side, all of our non-dy dx terms on the other side, at that point, what we can do is, since every term over on the left side of our equation here, in this case, there's only two of them, since both of these terms both have dy dx in common, we can actually factor that out of them. And the reason why this is a really important step is because once we pull the dy dx out of each of these terms, we're just going to have this one dy dx in front here. So that's just going to leave us with dy dx times sine of x times sine of y minus sine of y. So the reason why it's important to have to do this step and to get to the point where we only have one dy dx is because what we're going to be able to do next is basically just move all of the other stuff over to the other side of the equation, which is just going to give us one dy dx all by itself on one side of the equation. So now we can divide both sides by all of the stuff that we have in the brackets here. And that's just going to give us, let me move this up here. There we go. That's just going to give us dy dx equals cosine of x times cosine of y minus cosine of x all over sine of x times sine of y minus sine of y. So let me just make sure I didn't make any mistakes there along the way. Yep, seems to be good. Alrighty. Let's go ahead and go on to the next problem here. So the next one I wanted to do is to show you a little bit about related rates, because that is one of the top applications you'll see of implicit differentiation. And a lot of times that's kind of the hardest step of the related rates problems. So the problem we're going to do is we're going to have the altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters squared? So I think, when I first read this problem, first thing to kind of point out is altitude is a little bit of a, not super common terminology you see with triangles, but basically just treat that as the height of the triangle. So the first thing you want to do with these related rates problems is always going to be to draw a picture of what you're dealing with. There's generally 4 pretty simple steps that you're going to go through for all related rates problems. They'll pretty much get you to the answer every time. And the first is always going to be to draw a picture, because drawing a picture is really going to help make it a lot easier for you when we get on to the next steps and kind of figuring out what equations we're going to need to be working with. So obviously we have this triangle with the altitude of the triangle, so the height of the triangle, increasing at a rate of 1 centimeter per minute. So basically we know that it's growing at a rate of 1 centimeter per minute. We also know the area of the triangle is increasing at a rate of 2 centimeters squared per minute. So basically I'll just kind of draw that in here, 2 centimeters squared per minute. Okay. And then we're trying to find the rate that the base of the triangle is changing when the altitude is 10 and the area is 100. So one really important piece of doing your drawing is to kind of label different pieces in your drawing with a variable. So what we want to do is, in order to figure out what pieces we actually want to label, because you don't want to just go labeling everything all willy-nilly and just throw all these letters all around your drawing, because that's really just going to make things more confusing than it needs to be. What we really want to do is think about which measurements are actually going to come into play here. So the first thing that you want to do when you're kind of doing that is think about what is the measurement that the question's actually asking us to figure something out about. And in this case, it asks, what rate is the base of the triangle changing? So we know that we're going to try and figure out something about how fast this length right here is changing. So we know that we're probably going to want to label this side at some point. So I'll just go ahead and call this y. And since it's asking for the rate that this is changing, basically we know that what we're trying to find in the end is dy dt, which is how fast y is changing with respect to time. So this is our final goal here, is to find dy dt, given that we're labeling our base as y. The other thing we want to think about is what pieces of this triangle, or what measurements in our drawing, has the question actually given us some information about. So we have been given information about this height, or this altitude. We've also been given information about the area. right? We have not been given any information about the hypotenuse. So we're probably not going to consider that as one of the sides that we want to label here. We want to label our altitude or our height, and we want to label our area, because those are the things that we actually have some information about. And in fact, in this kind of final piece here where it asks us to find dy dt, it also gives us some more information, not only about how quickly these things are changing, but what their measurements are at the specific instant that we actually care about also. So we also know that the altitude is 10 centimeters and the area is 100. So since we know their actual measurements, the altitude and the area, and we know about how fast those two things are changing, those are probably going to be the other two things that we want to label. So we'll go ahead and just call the area capital A, and we'll call the altitude or the height of this triangle x. So the kind of moment or the instantaneous, spot in this triangle's growth or change in shape and all that we actually care about is going to be when our altitude is 10 centimeters. So when x is 10 centimeters, and when our area is 100 centimeters squared. So when our area is 100 centimeters squared. The units you really don't have to worry about too much when you're going through these problems. Technically that probably would be correct to label your units and use those in the equations, but as long as you're setting up your equation in a way that geometrically actually makes sense, those units are just going to end up canceling out and getting you, to the answer that you would expect based on the units that you've been given in your answer. So I'll touch on that a bit more. That'll probably make more sense when we get to the end. But all I'm trying to say there is I'm not going to worry too much about, there we go. I'm not going to worry too much about the units as we work through this problem. So once we have gotten our drawing and once we have labeled everything in our drawing that we're actually going to need to use, the next thing we need to do, the next step of these related rates problems, is going to be to come up with your equation that basically relates different measurements in your drawing or different measurements in the scenario that's being described. So in this case, we want to think about what kind of equation we can come up with that's going to relate the area of our triangle with the height and the base. Well, probably the best place to start, and of course, sometimes this takes a little bit of guess and check. You need to kind of come up with an equation, see how well it works, and if it doesn't work, come up with a new equation. But in this case, since we have area, base, and height, probably the best place to start would just be with the equation for the area of a triangle, which is that the area of a triangle is just 1/2 times the base times the height, which in this case is going to be x and y. So then once you've come up with your equation, what you want to do is you're going to take the derivative of both sides of your equation using implicit differentiation, and we're going to take the derivative with respect to time. It is possible that you may take the derivative with respect to something else, but I'd say like 99% of the time or more, you're going to take the derivative with respect to time, because these related rates problems, they're always going to be asking how quickly or what rate some measurement is changing, which basically what that kind of implies is that we are trying to think about how it's changing with respect to time. So you're generally going to take d dt of both sides of your equation. So this is, like I said, the implicit differentiation step, because we have these other letters here, a, y, and x, that we know are not the variable, right? Going back to the implicit differentiation problem we just did, we know, because we have this t down here on the bottom, that t is the variable. A, y, and x are actually functions of t, functions of time. So when we're taking the derivative of a, y, and x, we don't actually know the derivative of a, y, and x. So just kind of starting with the left side here to take the derivative of a with respect to t, since we don't know a, really, I mean, we know what a is in relation to x and y, but we don't know what a is in relation to t, which is our variable. What we want to do is just take the derivative with respect to time. Well, the best we can do really is to say that the derivative of a with respect to time is just going to be dA dt, because that literally just means the derivative of a with respect to t. So now to take the derivative of the right side of our equation, you can see again, kind of like our last example, we're going to have product rule here, because we have y times x, which are two separate functions. So when we're taking the derivative of 1/2 times y times x with respect to time, we have the product of these two functions here. So what we can do is just kind of keep this 1/2 out here, out front, and take the derivative of y times x and then multiply 1/2 times that whole derivative. So to do that, I'll again kind of do a side problem of product rule over here. So again, we want to figure out an f and a g. And again, it doesn't matter which one we call which. So we can call f our y and g our x. And then we need to find the derivative of each of these. So the derivative of f, the derivative of y, with respect to t is, again, just like we did with our a over here, it's just going to be dy dt. And then same idea here with g prime, the derivative of x with respect to t is just going to be dx dt. Okay, and now product rule again says that we're basically going to cross multiply these. So we're going to take f times g prime, g times f prime, and then add them together. So y times dx dt plus x times dy dt, and then we'll close our parentheses there. All right. So now once we have done this, once we have taken the derivative of both sides of our equation with respect to t, done the implicit differentiation step, what we want to do at that point is to actually start plugging in some of the values we know. Now, you want to be careful. You never want to plug in values before the implicit differentiation step. If you do, you're going to eliminate answers and you're not going to get what you should be getting. So to do that, some of these things we already know. We were basically given that we're looking at the point in time where x is 10 and where a is 100. So we already know that, at least x we already know. We don't really have, we don't have all these is what I'm getting at. We do have the rate of change of a and the rate of change of x, which I did right over here in our drawing. dA dt is always just going to represent the rate of change of a, how quickly a is changing. Well, we were given that the area is increasing at a rate of 2 centimeters squared per minute. So we know that dA dt, the rate that a is changing, is just going to be 2. So we can plug that in for dA dt. We also know that x, the altitude of our triangle, is increasing at a rate of 1 centimeter per minute. So we know that the rate of change of x is 1, so dx dt is 1. We don't know y quite yet. We can figure that out, though. So I'll actually come back to the dx dt in just a second. So first, let's think about y here. If we look in our drawing, y wasn't given. We know the moment in time we're looking at is when x is 10 and when a is 100, but we weren't given what y is. It didn't tell us what the base of the triangle was at the moment we want to look at. However, we do know a relationship between a, y, and x. We know that a is always going to be 1/2 times y times x. So we know that a, 100, is always going to be 1/2 times y times x, which is 10. So we can kind of set up this relationship and solve for x. So 1/2 times 10 is 5. If we divide both sides by 5, that gives us y equals 20. So we actually do know y, even though it wasn't given, we were given the information that we need to figure out what y is. Okay, and then dx dt, like I said, is just 1. And then we have plus x, which we are given that we want to look at the moment when x is 10. So we're going to put in 10 for x. And then times dy dt. Well, remember, dy dt was the thing that we were looking for. That was our goal all along. So obviously we don't have that at this point. So now we have this equation, which we have plugged in all the information we know. And we have this, at this point, this equation, which only has dy dt, which is the thing that we're looking for, and then a bunch of other numbers. So now we have a single equation with a single variable. We should be able to just solve for the thing we're looking for, and that should be our answer. So we can just kind of simplify this. We will have, we can multiply both sides by 2 to cancel out the 1/2. So that'll give us 4 equals 20 times 1, which is just 20, plus 10 times dy dt. Then we can minus 20 from both sides, giving us negative 16 equals 10 dy dt. And then we can divide both sides by 10, which gives us dy dt equals negative 1.6. And now this is kind of what I was getting at earlier, where the units come into play. We are being asked to find at what rate the base of the triangle is changing. Well, since the base of the triangle is a unit of measurement that we would use centimeters to measure, the rate of change of centimeters is going to be centimeters per minute, because we know that these other rates of change were measured in minutes. So basically we know that it's going to be changing at a rate of centimeters per minute, just like this other side length was. So we can go ahead and say that it was changing at a rate of negative 1.6 centimeters per minute. So in other words, in order for the area to increase by only 2 square centimeters per minute, if this side is increasing at a rate of 1 centimeter per minute, this side would actually have to be shrinking, because it has a negative rate of change at a rate of 1.6 centimeters per minute. If the question asked us how fast is the base of the triangle shrinking or getting smaller, we would then make this positive and just say 1.6 centimeters per minute. But since it just asked what rate is it changing, we would want to make sure to keep that negative on there. All right. Well, thank you all for the positive comments. We'll keep it going here with this, and hopefully keep helping you out a bit more. Like I said at the beginning, I know maybe some of you have been kind of joining in a little late after the start here. If you have any questions along the way, feel free to type them in the chat. I'll do my best to answer any questions. Unless with no questions on those, though, we'll go ahead and jump into this other example that I had prepared for you guys. So going back to implicit differentiation here a bit, this one is going to kind of build again a little bit off of the first problem that we did in terms of the methods we're going to be using. Obviously, this one's not going to get into related rates, though. So the problem we're going to be doing here is use implicit differentiation to find an equation of the tangent line to the curve at the given point. The equation that we are given is y times sine of 2x equals x times cosine of 2y. And the point that we are given to find the tangent line at that point is pi over 2, pi over 4. So the x coordinate of pi over 2, y coordinate of pi over 4. So really with these types of problems where you're asked to find the equation of a tangent line to the curve at a given point, it's going to take the exact same process as the first problem we did here. And it's just going to build on that a bit. So what you want to think about basically is we're going to start obviously with just implicit differentiation. So if you're not really told which letter is your function and which letter is your variable, you know, sometimes it may say find dy dx. In this case, they didn't do that. They just gave us some equation with x's and y's. Typically, you can assume that x is going to be the variable and y is going to be the function. And the reason for that, and of course, that's assuming that you are given some equation that has x's and y's. The reason for that is typically a function with x's and y's is going to be graphed on an xy axis, where x is always the independent variable, the input variable, and then y is always the dependent variable or the output variable. So as a result, we always want to take the derivative of both sides with respect to our variable, which, since we're going to be able to assume that x is our variable, we'll take the derivative with respect to x. So again, this is another example where we're going to have to apply product rule. And in fact, we are actually going to have to apply product rule and chain rule on this one. So this is going to be kind of an interesting example. So you can see on both sides of our equation here, we have a product of two separate functions. So we're actually going to have to do product rule twice, once on each side of our equation here. So we'll start with our left side. We're going to again, break it down into f and g. So f we'll just say is y. G we'll say is sine of 2x. F prime is going to be the derivative of f, which, again, since we have our function, we have our function we're taking the derivative of with respect to our variable. Since we don't know what our function is, the best we can do is to say the derivative of y with respect to x. Then we're going to find g prime, which is just the derivative of sine of 2x. And to find the derivative of sine of 2x, we're going to have to use chain rule. So the chain rule says take the derivative of the outside function, which is going to be the sine. Since we have this 2x within the parentheses here, it's usually going to be what's in the parentheses like that. That's going to be your inside function. So our outside function is the sine piece. We're going to take the derivative of sine. So the derivative of sine is cosine. And then we're going to leave the inside function alone, so leave 2x as 2x, and then multiply that by the derivative of the inside function. Well, the derivative of 2x is just 2. And then by product rule, we have to cross multiply these and then add them together. So y times cosine 2x times 2, so that'll just give us 2y cosine of 2x, and then plus sine of 2x times dy dx. And that'll be the derivative of the left side of our equation. So now on the right side of our equation, we are again going to have product rule. So we'll go ahead and just call f the x function here, and we'll call g the cosine of 2y. Then we need to find our f prime and our g prime. So the derivative of x is just going to be 1. And then the derivative of cosine of 2y is going to be a little bit more complicated because unlike over here where we had just our variable, just x's, taking the derivative with respect to x, over here we have y's. We have our function. So the derivative of cosine 2y is going to be a little bit more similar to taking the derivative over here. So again, we're going to have chain rule because we have this 2y being plugged into the cosine function. So first of all, we're going to take the derivative of our outside function, which is cosine. The derivative of cosine is negative sine. We're going to leave our inside function the same by chain rule. And then we're going to multiply that by the derivative of our inside function. Well, the derivative of 2y with respect to x is just going to be 2 dy dx. Since we don't know y, again, we can't know its derivative, but we can say the derivative of y with respect to x. So then by product rule, we will cross multiply these. So we will get x times all this stuff. So we're going to have negative 2x. So the negative 2x times sine of 2y times dy dx. And then we're going to have 1 times cosine of 2y, which is just cosine of 2y. So then we're going to add in cosine of 2y, and that is due to the product rule. So now we've taken the derivative of both sides of our equation. So now what we can do, just like we did before, is we're going to move all of our dy dx terms to one side of our equation. We'll go ahead and move it over to the left, and all of our non-dy dx terms over to the right. So we'll put our dy dx is to the left. This term is going to have to move over to the right. So we're going to minus 2y cosine of 2x from both sides, minus 2y cosine of 2x from both sides. And then we need to move this over to the left. So we're going to add 2x sine of 2y dy dx to both sides. So plus 2x sine of 2y dy dx. And what that is going to do is it's going to cancel this over on the right side of our equation. It's going to cancel this over on the left side of our equation. And we are just going to have 2x sine of 2y dy dx plus sine of 2x dy dx And then we will set that equal to what we have over on the right now. At this point left is the cosine of 2y minus 2y cosine of 2x. All right. And then once we have all our dy dx terms over on the left side of our equation, again, what we can do is factor out our dy dx, because now both of these terms have a dy dx in common. And that's going to accomplish exactly what it did in the first problem we did here today. And that is going to be making so that we only have a single dy dx term left that we can then solve for much more easily. So if we take dy dx out of this first term, we're going to be left with 2x times sine of 2y plus sine of 2x. And then on the right, we're still going to have nothing different. And then we can divide both sides of our equation by everything within the parentheses here, because dy dx times all this stuff, we can divide it over to get the dy dx all by itself. So our numerator is just going to be whatever we had on the right before. And then plus 2x sine of 2y plus sine of 2x. So there's our dy dx. But remember, there is a little bit more to this problem, because what they told us to find was the equation of the tangent line to the curve at the given point. So now we have dy dx. Well, what you want to think about is, what is a tangent line? Well, a tangent line is just a line that shares two things in specific with the curve that you're making the line tangent to. So those two things are going to be that it has to share a point, it has to go through the same point, and not only that, at that specific point, it has to have the same slope. So it needs to share a point and share the slope at that point. So in order to figure out the equation of the tangent line, we need to make sure we come up with an equation of a line that has those two things in common. Sorry about that. Seems to be working now. Yeah, so we need to come up with an equation for a line that has those two things in common. Shares the point, shares the slope at that point. Well, the reason that we had to find dy dx is because what dy dx represents is the slope. We don't know what this function is in terms of, having y equals some function of x, but we do know that it's given by this curve here, this relationship between x and y. Well, we also know, based on the fact that we just found this dy dx, that this equation right here will tell us the slope of our function at any given xy pair that we plug in. So basically, if we plug in pi over 2 for x and pi over 4 for y into this equation here, that'll tell us the slope of our function at any given point, or in this specific case, at the point that we care about, pi over 2, pi over 4. So if we plug in the point pi over 2, pi over 4, which means wherever we see a y in this equation, we replace it with pi over 4. Wherever we see an x in this equation, we replace it with pi over 2. That'll give us the slope of this curve at this point. Well, if we do that, I'm not going to go through all of that. You can kind of see some of these terms are going to cancel out. It's not going to be terribly difficult to do that because, like, for example, right here, cosine of 2y. Well, cosine of 2y is just going to become cosine of pi over 4 times 2, which is cosine of pi over 2. Cosine of pi over 2 is 0. So same thing is going to happen here with sine of 2x. Which means if we do go through all of this and plug in this for x and this for y throughout this whole thing, what that is going to simplify down to is we are going to get, in the end, pi over 2 on the numerator. So this whole thing on the top here is going to give us pi over 2. And then our denominator is going to simplify down to pi. So when we plug in these on the bottom here, it's going to simplify down to pi. Well, this is the same as pi over 2 times 1 over pi. Because remember, dividing by something is the same as multiplying by its reciprocal, or 1 over that thing. So pi over 2 times 1 over pi is the same as pi over 2 divided by pi. Then these pi's cancel, and we just get 1/2. So basically, we know the slope of our tangent line needs to be 1/2. We also know that it needs to go through the point pi over 2, pi over 4. So if you know the slope of your tangent line, and you know the point that that tangent line has to go through, well, you can just use the equation of a line, the point slope form, which is y minus y0, which is just some y coordinate that your line lies on, equals the slope times x minus x0, which is the x coordinate of some point that this line lies on. So we can replace y0 with pi over 4. We can, sorry, I don't know why that keeps happening. We can replace m with the slope that we just found here, 1/2. X is just going to stay as x, and then we can replace x0 with the x coordinate we know that this needs to go through, which is pi over 2. Then we can simplify that, and doing that, if we simplify it and get the y all by itself by adding the pi over 4 over, we're just going to get y equals 1/2 x. Yeah. So this is going to be the equation of our tangent line, which goes through this point. We know that it shares the point. We know that it's going to have the same slope because we found the slope using this dy dx. Therefore, that's going to be the solution to this problem. Just going to be y equals 1/2 x is going to be the equation of the tangent line. So those are all the problems I had prepared for you guys today. Not seeing any questions, so if nobody has any, we'll go ahead and wrap things up here. Thanks for joining. We're going to keep working on these live streams. Going to try and do one every week. Hopefully they'll keep getting better as we go along. If you have any suggestions, feel free to drop them in the comments. If you found this video helpful, please be sure to give this video a like on the way out. Oh, I actually do see a question popped up here. If you have any questions from a different topic, yeah, maybe if it's a kind of a quick one, we could definitely might be able to help you out real quick. But what kind of question did you have? Go ahead and drop your question in there. I'll see if I can help you out. I'll just keep this up on the screen here if anybody wants to look back through that. Okay, so question about how you can know if an equation has a root in a given interval. So, really kind of depends on the equation and how you might know that. But in general, what a root is basically a solution to the equation. So typically we would see, or I guess I should say, basically where y equals 0. So a root is just going to be where a function intersects with the x-axis. So if you're trying to find, where a root of the equation is, it's just going to be where y equals 0. So, to actually find the root, you would just plug in 0 for y and solve for x, basically. In terms of how to know that it must have one within the interval, that really kind of depends on the equation. But basically what it comes down to is, proving that equation has a solution when y equals 0 within that given interval. All right. Perfect. Yeah, we'll go ahead and wrap things up there. If you guys wouldn't all mind giving the video a like on your way out, that's the best way to help out with these, because YouTube will see that and show it to more people, so we can get more people on these live streams and get some more questions in here too. So thanks everybody, and see you next time.